Inside a garage in Chicago, 12-year-old Sabrina Pasterski spent her time assembling a physical airplane from raw materials and instruction manuals. There is a rigid, satisfying logic to physical engineering. You follow the steps, you put in the hours with pop rivets and fiberglass, and you produce a working machine. That tangible work led to a clear outcome. She flew solo at 14 and set her sights on building a spacecraft that could reach Mars. At this stage, Sabrina viewed science as a pragmatic tool, a necessary stepping stone for creating advanced physical technology. Society often repeats a dominant myth that studying fundamental theoretical physics provides a direct path to inventing the physical future. Tech billionaires and prestigious institutes frequently claim that understanding quantum mechanics naturally yields quantum computers or more precise GPS systems. Guided by this assumption, Sabrina left aerospace engineering to major in physics at MIT, intending to invent the next wave of transformative technology. She quickly encountered a jarring reality. In the world of string theory and quantum gravity, there are no blueprints, no physical machines, and no black holes nearby to test a theory against. Without physical experiments to run or machines to build, the daily life of a theoretical physicist looked entirely different than the one she had imagined in her garage. In this ecosystem, mathematics is the only laboratory. Without physical tests, every theory is built and vetted through equations alone. This reliance on math forces the field to depend on pure consensus and mathematical taste to determine what is actually interesting or valuable. This environment creates a specific risk. Without physical proof to ground the work, mainstream hype can quickly outpace academic reality.
Sabrina experienced this when Stephen Hawking cited her research, triggering a wave of mainstream press and 30 under 30 lists, attention that many in the academic community view with suspicion. This led to a profound sense of imposter syndrome. She felt a crushing pressure to master an infinite mathematical landscape through book learning alone. Surviving this environment required moving past the shut-up-and-compute engineering mindset to find a new way of understanding the purpose of the math. A moment of wonder. Sabrina eventually arrived at a foundational epiphany. Theoretical physics functions as a science of data compression. On the surface, the physical universe presents itself as a completely chaotic, infinite storm of interacting particles and forces. Physics uses the standard model to extract order from this chaos, distilling it into a few elegant rules. Concepts like symmetry let physicists reduce the data needed to describe a system. Understanding rules for one isolated system means we don't have to measure everything. Quantum gravity and string theory are simply attempts to compress the laws of the tiny quantum world and the massive scale of general relativity into one master framework. The ultimate output of a theoretical physicist is a self-consistent, highly compressed mathematical framework of reality. Now a faculty member at the Perimeter Institute, Sabrina has begun applying her engineering mindset to the bottlenecks within the math itself. She views the decades of accumulated physics literature as a massive data set rather than a textbook to be memorized. To tackle this, she has started building cross-disciplinary teams at Perimeter, pairing physicists with computer scientists and software engineers. Her team uses semantic search to scan the literature for redundancies or dualities. This automates the discovery of links between different branches of math that individual researchers might never see. Treating the math as an engineering challenge allows the field to move past the traditional model of a lone genius working with pen and paper. We have to stop justifying theoretical physics by demanding it immediately produce consumer gadgets. The field has a specific purpose: decoding the foundational laws of nature. This shift toward a data-driven, collaborative approach represents a change in how we explore the structure of our universe. By mapping these laws, theoretical physicists provide the instruction manual for future engineers, who will build the spacecraft that take us to the stars.